we were left with, we finished the thermocouples as one of very important temperature sensors. And today we will cover the other sensors, which is basically the thermistors and the RTD with some details. And we will talk about finally very brief two other types of temperature sensors. So by the end of this week, now we are done completely with the temperature sensors. So thermistors, what are thermistors? What do you mean by thermistors? A thermistor is a resistor whose resistance change with temperature. And this is the nature that any metallic structure, when you increase its temperature, its resistance will change. Okay, so the thermistor will utilize this important property to have this type of sensor. Now you can see here, these are some examples of thermistor. This is the head of the thermistor, and these are the two leads. These two leads, we'll use them to do some measurement. We'll see we will measuring what, but this head is where you coming close to the object that you want to measure. And those thermistors are extremely small, and you have them in your kit. So you'll see them, they are very, very small, tiny. So you can have them in a circuit without really doing any interruption. It's not big ones, and they can be easily connected to your circuit. Now, these are resistive elements. So this is again part of the resistive sensors. There are made from metal oxide ceramic containing different materials, copper, nickel, cobalt, etc. And they are covered, packaged. What you see here, you don't see the actual sensor that sense the temperature and change it into a change in the resistance. But what you see here is a bead of glass that covers this, and this bead of glass act as a protection, so to protect the internal elements from any physical damage. But these beads of glass are conductive, thermally conductive. So the heat can be easily transferred from the surrounding to the sensors inside through those beads, that they act mainly as a protection. Now, suppose that we have a 1 kilo ohm thermistor. You go and you buy from the market 1 kilo ohm thermistor. What does this mean actually? This means that at room temperature, the resistance of the thermistor is 1 kilo ohm. Remember, when we talk about the strain gauges, we said the strain gauge mainly is 120 ohm when no stress is applied. Now, what will happen here to the thermistor if we increase the temperature? Now, the thermistors has some unique properties that is different than many metallic structure, that their resistance will drop as you increase the temperature. So most of the metals, as you increase the temperature, and we will see that in the RTD, which is another resistance that change with temperature, but the thermistors, they have this negative relationship. So as you increase the temperature, the resistance decreased in an exponential way. So as room temperature, the reference temperature, yeah, room temperature, which is 22 degrees centigrade, that this is the reference temperature, and we will see this in the coming formula for the thermistor. So if I want to find a mathematical relationship that can model this line, so R is equal to R0. R0 is the temperature, sorry, the resistance at certain temperature, which is usually the room temperature, is equal to, so the R is the resistance at the temperature of interest, okay, equal to R0 e to the power, so this comes here the exponential, you can see here the exponential, 1 over t minus 1 over t0. T now is your unknown. This is your unknown. This is what you are looking for. Okay, and everything else given. You measure the resistance at this temperature. you know R0, this is an T0, these are giving, and you know beta. Beta is a constant, depends on the type of the thermistor. We said the thermistor made from different materials, so based on the different materials you will have different types of temperature, sorry, constants, beta. Okay, so basically you have this mathematical formula. Now to find T0, you can find, sorry, you want to find T. Usually what we do, we'll take R divided by R0 equal to E the power of beta 1 over T minus 1 over T0. Take the ln for both sides. So ln R over R0 equal to beta 1 over T minus 1 over T0. Then you need to solve this equation for T. This is how we solve it if we want to solve it mathematically. But we mentioned in the strain gauge that measuring the resistance is not really very practical. And to be able to do the measurement, what we do, yes, we need to use the Wheatstone bridge again here. So another example of the Wheatstone bridge is the thermistor. Okay, we don't like to continuously monitor the change in the resistance, because we said that to have a continuous system that can measure the change in the specific phenomena, we prefer to do that by measuring voltage, because all the measuring systems that we have, it's either a voltmeter, oscilloscope, data acquisition cards, all of them, they measure voltage, they don't measure resistance. So here, for example, your thermistor will be here in one of the resistors, and then the rest will be the other resistors. So for example, if we have an RTD that is temperature, sorry, its resistance is 1 kilo ohm at room temperature. So basically, we will select the bridge to be balanced. So we will have R4 over R3 equal to RT over R2. Now you could have all of them the same resistance, or just maintain the ratio. Up to you. Depends whatever resistors are available. And now one thing here you have to know that this resistance physically does not connect to the bridge. I mean, sorry, it's not uh, in the same proximity. Okay, they are physically connected, but they are not in the same proximity, because this sensor, which is the RTD, which is something like this, as I have shown to you, this RTD will be measuring something, maybe some burner, some oven, so it will be far away from the Wheatstone bridge. So basically you have those leads that will be extended and connected between these 2 points. So this is something very important to understand. Now, as we know that once you start to increase the temperature, the resistance will start to drop following this exponential decay. And for this specific sensor, your E0, this voltage, now the arrangement here of the resistors are a little bit different than the one that we have seen in the Western bridge. It does, sorry, with the strain gauges. It doesn't really matter how you arrange the resistors. The formula is exactly the same thing. So here E0 is your output voltage, is equal to E excitation, which is this voltage. Now, if you take this, just rotate it 90 degree, so you'll see that R4 and R3 are in the same leg, RT and R2 are in the same leg. So this is why we call it RT plus R2 divided by R4 plus R3. Remember, we divide by the summation of the resistors in the same leg, and then we multiply RT in front times the resistance in front of it. So RT times R3 minus R2 times R4. So this will be the formula. Now, if RT increased or decreased bar delta T, depends, are you increasing the temperature or decreasing the temperature, then your excitation will have this formula. Okay, so you multiply this minus R4, R2. So this will be your output voltage. Okay, now remember this RT times R4. This one, this will becomes RT plus delta RT times R3. Now, RT times R3 is the same as R4 times R2. This will cancel, so this is what is left. Now, I cannot ignore delta RT here in the equation. Why? Because delta RT is large, it's not small. Remember, in the strain gauge, the change in the resistance, you are talking about a fraction of an ohm. But let's go back to the curve here and see. So for example, if my temperature increased only from 330 to 340, that's it, just 10 degree. Let's see how much the change in the resistance. So the resistance, let's say it was around 300. Now when you go here, it goes to around 220. So it's like 80 ohms change happened. So this curve is very steep and very sensitive. I will be posting a small video about measurement of the resistance of the thermistor, as I did for the string gauges, and you will see that by just touching it, rubbing it by my hand, the temperature drops very, very, very fast, and it drops. This is one thing important about this, the thermistor. It's very responsive. The response time is extremely fast, and you need sometimes this to happen in your sensor. But also you'll see that the resistance drops drastically by just rubbing it by my hand, which is, this is why in this sensor, unlike the strain gauges, delta R cannot be ignored. It's extremely important. Now, in the strain gauge, you could also keep the delta R and don't ignore it, and to get the exact number, that's absolutely okay. There's no one can say this is wrong. However, if you want to have a nicer mathematical formula, then we will ignore the delta R. That's all. Okay, that's all for the thermistor. Let's move to the RTD, or resistive temperature detector. So basically, the main material we use is platinum. Okay, so what is a platinum RTD? Platinum is basically a coil, a very thin wire made from platinum, and the platinum resistance is a function of temperature, same like the thermistor. But here, one thing interesting here, as you increase the temperature, R increases. There, as you increase the temperature, R decreases. The thermocouples, as you increase the temperature, the voltage increases. So each one has totally different characteristic. In the thermocouples, we don't need any Weston bridge because we are measuring the voltage directly. In the thermistor, on the other hand, we need the Weston bridge to convert the change in the resistance into a change in the in the uh, uh, into voltage. Do we always have to start with a balanced bridge? Yes, we always start with a balanced bridge. So we start with a voltage equal to 0. Now, once we start to sense voltage, it means that our sensor start to detect a change in the temperature. Now, when you see to this relation, it's a non-linear relation because of the square. So you can see here there is a square. R0 is the resistance at 0 degrees centigrade. Now, if you want to find T greater than 0, your R. If you want to, then this is the formula that you use. Then A and B are two constants. This is A and this is B. And this is our constant for platinum. And platinum is the main thing, is the main material we use it for RTD. So you will not see too many different materials used as an RTD. This is just basically those constants is the calibration. Remember, we said always we need to calibrate. There is a physical phenomena that we measure, and there is the voltage or the electrical parameter, the resistance. So here, the change in the temperature is reflected as a change in the resistance. So people, they came and experimental this, and they start to increase the temperature and see the change in the resistance. Change the temperature, see the change in the resistance, and then they come up with the formula that fits these points that you start to do. Okay, so then they came up with these formulas. So these are coming from experimental values. Let me explain more. So basically you will have here, this is like experiments. You bring a wire, the platinum wire, and this is your temperature, and this is your R. And then let's say at 50 degrees centigrade, you find certain R, 1 point. At 60 degree, you will have another point. At 70 degree, another point, and move on, and so on. Then you come up with a curve. This is called a polynomial curve. And I believe you guys are studying numerical method. You will study something called interpolation, and and curve fittings. So how to find a curve or a line that goes through all these points. Okay, so then you have to come up with a formula for this. And in this formula, you decide what is the degree of the polynomial. Is it first degree, second degree, third degree? And then you can find those constants. Okay. And in Excel, you have this actually. Excel, you have built-in polynomial curve fitting functions. So if you have points and you want to find the curve that go through those points, it will give you all these constants. It depends on your points. Okay, let me see. I have a couple of questions here before we move any further. Okay, here. Okay, does resistance always increase with? Yes, except for the thermistor. Okay, for RTDs, it's always there. Now, you can see here that the B factor is much, much less than the A factor. So we can ignore it. So this quantity is very, very small value. So we can ignore it and have the linear relationship instead. And when you see the curves for the RTD, they look like a very, very linear material. So let's see this simple example. Here we have a platinum RTD measures 100 ohms at 0 degree. So at 0 degree, it is 100 ohm. And 139 ohm at 100 degrees. So for the span of 100 degree, you have a 39.1 change in the resistance, which is a good thing. We know now from the sensor that we want to have more sensitive sensors. So the higher within the range, you want to see a more change in the electrical quantity. So it says here, find the resistance at 50 degrees centigrade. So we know that R at 50 is equal to R at 0, 1 plus A times T. Okay, so at 50 degree, we want to find this. Okay, now this is, as we know, is 50. A is known to us. R0 is 100. So just substitute, you will get this is 119.55 ohms. So at 50 degrees centigrade, your resistance will be 119.55, which is something in between the 0, which is 100, and the 100, which is 139, which is almost in the middle between the two. And in the middle means that it's a linear relationship. So 50 is between 0 and 100, then 119.55 is the middle between 100 ohm and 139.1 ohm, which shows you that this is very, very linear relationship. Okay, what is the temperature when the resistance is 110 ohm? So if I'm measuring 110 ohm, what will be the resistance? So 110 is equal to the 100, the resistance at 0, 1 plus the A, which we know, times the T that we don't know, this temperature. So this is the only unknown here we have. And if you calculate, you will find your T is equal to 25.58 degrees centigrade. And this is usually what we want. Usually we know this value of the resistance, and this is the unknown that we want to find. And here's the solution. So how we do that physically? The circuit that we use for RTD is a little bit different than the circuits we use for the thermistor. So basically here, we to measure this resistance, we apply a constant current. So we have a current source, and we apply this constant, and we measure the voltage across the resistance to find the resistance, because I am posting certain current. I am measuring the resulting voltage, Ohm's law. So your R is equal to V divided by I. So this is how we do for the RTD. And if you see here, the relationship of the RTD is basically very, very linear, and we have a curve here that will show this. Now, why RTDs? Why not thermocouples? Why not uh, thermistor? We will see more details here, but here are some of the advantages of the RTDs. First, they have a good range from minus 200 to 850 degrees, so they have wide range. Good accuracy. They are better than the thermocouples when it comes to the accuracy. They are linear, so they are better than the thermistor when it comes if you want to have a linear behavior. Also, they are very, very stable material. So if you look here to the curves, this is the temperature, and here is the resistance. So you see here, this is the thermistor, how it is going down exponentially. This is the platinum, goes straight line. The nickel or the bulk you see here, this is the exhibit some non-linear behavior, but the platinum is straight line, and this is why we can approximate the platinum as a linear function, which is something really good in your sensor. How it is made, the RTDs, there are two different ways to do that. You see here there is a thin film layer. You can see here this is a thin film. So basically what you do, you have a substrate from ceramic, use what we call etching technique. You make grooves in this substrate, and then you deposit the platinum there in these grooves. And of course this is done, very precise systems are used to that, to have exactly very precise width, length inside, so that you know exactly what is the resistance you are getting at room temperature. And then these wires are coated to protect the platinum wire. So here, this is how they look like. So there is sort of like of a coating on them that is to protect what is inside. And here, this is how it look like. Sometimes you have them as a wire wrapped around a glass or a ceramic material, and then it's covered, so that again for protection. So these are the two different forms that you will have the RTD. This is a very nice slide I found. It compares the thermocouples with the RTD with the thermos. Let's look into each one. So this is the thermocouples, and we know what does exactly this means. The thermocouples, it's two wires connected from one side, and the other side we measure the voltage, and it is a relation between temperature and voltage right away. And it is a bit nonlinear. We said that we can have up to the ninth order polynomial to represent the relation between the voltage and the temperature. So what are the temperature? It's very simple, very simple. Wire, a piece of wires, heat it in one side, or whatever temperature you want to apply, measure the voltage at the other side. So it's a very, very simple. Rugged, it's very robust. It's a wire, it's a metal. You don't need to worry about it. And I have shown to you, you can just throw it, you can do whatever with it. It's a wire, nothing will happen with it. Inexpensive, it's very cheap, by the way. If you go, it's a couple of bucks, that's all, the cost of them. No external power. This is something very important. Remember, in both the thermistor and the RTD, we have to use an external voltage source to measure the resistance. In the case of the thermistor, we need to have the excitation voltage for the bridge. In the case of the RTD, we need to have an external current source to measure the resistance. Here, there is no power source. So that will make it very cheap system to do the measurement. Wide range, we have seen it's a huge wide range of measurement. And there are a variety of styles, K-type, T-type, there are different types of those. Now, what are the disadvantages? Non-linear, and this is, I said, ninth order polynomial, which is something bad to come up with a function that represent this to predict the value. It's not easy. And worst thing is the small sensitivity. We have shown that for the whole range, which is could be 1000 degrees centigrade, you have only 50 millivolt change. So it's a very, very little change in the voltage, which is make it insensitive. So this is a big disadvantage of the thermocouples. Now, small output voltage, it's clear, requires CJC. This is junction compensation. You need to do some temperature compensation. What does this exactly mean that you need to do junction compensation? We will not go in details, but this is just to explain the terms to you. Now, when you have we mentioned that little bit during the thermocouples. We mentioned that you need to compensate for the temperature at which the sensor is located. Okay, what does this mean? Remember, we said that, okay, I'm measuring the temperature, the sensor as at one side, the measurement system is the other side, okay? And then we are measuring the difference between the two. So I have to compensate for the junction point by adding the voltage that is produced by the temperature at the existing or where the system is does exist, least stable one. Now, when it comes here to for the RTD is a temperature, sorry, is a resistance. So it has a temperature with resistance, and the resistance increases. It's the most stable one, very, very stable, very good linearity compared to all the others. And this is the most accurate one. Again, it has low sensitivity. Okay. It needs to be externally powered, so it is costly. And the output resistance still is not very high, as we have seen for 100 degrees centigrade it is like 39 ohms, but it's better than the thermocouples. Now, when it comes to the thermistor, you will see in the video that they are very, very fast. If you want to have a fast sensor among the three, they are the fastest. Just touch, you see a response immediately. High output, and this is the lead resistance are the lowest in terms of giving us a certain error. They have limited range compared to these two. The thermocouples and the RTD give you much wider range. This is again like the RTD, they are externally powered. They are very nonlinear. They are more fragile. We said that they are covered with a bead of glasses, so those one can break compared to the RTDs, and of course the thermocouples are the most robust one. So these are some of the advantages and disadvantages between these three different sensors. I have a couple of two slides only. The first one is what we call integrated silicon linear sensor, and that is similar to what you'll be using. You will have two different type of sensors. You will have the thermistor, and you will have the integrated silicon linear sensor. So it's basically here, it's a microchip, okay, and it has three terminals. In one terminal, it will be grounded, connect to ground. Other one, you will supply voltage to it. You will supply between 3 to 5.5 volt. And then you measure a V output. So you measure a V output. And now this is the sensor. Now it has been found that the V out is a function of the temperature. So it has certain linear formula. It's equal to 400 millivolt plus T minus 0 times 19.5 millivolt per degree centigrade. So this temperature that you want to measure. So, and this is how physically the sensor look like. So then you take your output directly to the microcontroller. So this is a three-terminal device. It's relatively simple to use, and it's very cheap again. Can be easily integrated with a microcontroller, as I mentioned, and you will do some experiment if you don't already done some experiments there. The voltage is linear, as you can see here. Now, what are the disadvantages? Compared to all the three other sensors, they are less accurate, operate over a very narrow temperature range. They don't go for extreme temperature either in the negative side or the positive side, and they are less responsive than them. Okay. So, but they are good in certain applications. For example, if you want to monitor the temperature of inside your house, you don't need to have something very responsive. You need to have something that is cheap. You need to have something that is doesn't cover wide range of temperature because you don't need that. So it has its own application. Now, all the previous sensors, they are the sort of called contact type of sensor, meaning that you have to come in close proximity between the sensor and the object. You have to touch it. Okay. Now, sometimes that's not feasible. You cannot touch the object. For example, if your object of interest is energized with electricity, there's a high voltage there, and personally, I use that. Sometimes I need to take the temperature of the insulator, which is energized by 400 kilovolt. How I can do that? There is no sensors of all the ones I mentioned can be used in this application. I have to stay far away from the object, and still yet I need to take its measurement. So how we can do that? We use the infrared temperature sensor. Now here, the objects, all objects radiate an infra, which is below the visible spectrum. So you need to have a special sensor, and you can see them in the movies. When you look here, you see the object that is hot, it's reddish color, and the object that is not hot, it is bluish in color. Okay, so depends on the temperature of the object, you will see different colors. And here is a heat source. It will radiate these infrared, and here is the sensor that you can have here, and it will detect this infrared. The higher the temperature, the more infrared will be emitted and will be captured, and then you need to calibrate to tell, okay, for this amount of infrared received, this is the temperature. And they come up like something like this. Sometimes it's like a gun, and you just point with a laser beam to the object, and you just press this button. Okay, and then it will take the temperature. Some of them, they are very accurate, and they are, as I said, they are very important when your application doesn't allow you to come close at all, even you or the sensor may be damaged when you come up with such high voltage. So that's all. So as I mentioned, I tried my best not to cover too much material. And on Monday there will be no class. Of course, it doesn't make any sense to give you a class on Monday, so there will be no class, and we will resume our classes at full speed on Tuesday. Please, if you have any questions, if you have any things that you want to discuss, just please let me know.